now introduce you to Feryal Ozel, who's a professor of astronomy and astrophysics in astronomy. She's made pioneering contributions to the physics of neutron stars and black holes, as well as the coevolution of black holes and galaxies in the universe. Feryal is a fellow of the American Physical Society, current Guggenheim Fellow. She received the Maria Goeppert-Mayer Award from the American Physical Society, the Radcliffe Institute for Advanced Study Fellowships, the Bart Bok Prize from Harvard, and the Miller Institute Professorship from Berkeley. She serves on a large number of committees for NASA and the National Science Foundation. She's a chair of the Science and Technology Definition Team for NASA's next large X-ray mission, Concept and Links, and she frequently appears in TV documentaries on PBS, BBC, and the History Channel. Please welcome Feryal Ozel.
Thank you. Good evening. It's very nice to see so many of you here. And that guitar performance is hard to follow, but I'm hoping to do my best and take you on a journey tonight with me for the next 45 minutes or so to what we call the extreme. So extreme places in the universe, extreme places in astrophysics, where you might think science meets science fiction. Is this really science? Are you sure you're really an astrophysicist? And I'm going to ask questions like, what makes up the cores of neutron stars? Don't worry if you don't know what a neutron star is right now, or you're not sure exactly what a black hole is right now. Hopefully by the end of the talk you will know these. And more importantly, maybe we'll be able to answer the questions like, what particles make up the cores of neutron stars? What is the dividing line between more or less matter as we know it, even if it is in a state that we don't recognize on Earth, and what we call a singularity, where black holes appear? And are black holes really what we predict? Do they really have event horizons that cut them off from the rest of the universe? So these might be some far-fetched questions, but really there are underlying reasons why we ask these questions. For example, we want to know if our theories of physics fail somewhere. We can design experiments, we can think of mathematical frameworks in which we explore physics. And we try to push it to their boundaries. And the universe provides us with ample places where we can actually really push that frontier and say, do they break somewhere? Is there something else that appears that we don't know of yet? Do they contradict each other? We have different physics theories that describe the subatomic, like you heard in Keith Dennis's lecture last week if you were here, and I will introduce it again a little bit today. And gravity that acts on the scales of stars and galaxies and the entire universe. Is there ever a tension between these, and can we exploit that tension in order to further our understanding of physical reality? And other questions like, what experimental evidence do we have for the physical theories that we write down here, mathematically formulate? Because physics, after all, is based on evidence. It is based on facts that are based on experiments. So whatever we can think of, we would like to see it in order to believe it. We would like quantitative data in order to really move forward. So this is going to be the backbone of my lecture. Can we break as we move to the brink of a black hole, the edge of a black hole, going from a neutron star to a black hole, can we break our theories? It might sound weird, but that's actually something that excites me. So before we go too far down that rabbit hole, though, let me bring you back to Earth, where we know what atoms are made of, and we can test a lot of our theories experimentally. So this is where Keith Dennis left off. The building blocks of normal matter where we know matter is made up of atoms with nuclei that carry most of the mass, and a cloud of electrons around them that make up most of the volume. So anything from water to one of the densest elements on Earth, platinum, just has the structure. And platinum and water differ by density by only a factor of 20. You might think 20 is large, just wait. So under these circumstances, there are protons and neutrons that make up matter. Now, there are places in the universe where we start crushing matter further and further under the weight of gravity. And at that point, the electrons that make up the bulk of the volume get pushed into the nucleus and start combining with the protons, making more and more neutron-rich matter. So at that point, we have, if you will, a neutron soup that is still, in some ways, reminiscent of the nucleus. It's just that the density has increased by a very large factor. All the electrons are now in the nucleus, and this matter that we call neutron matter is now extremely dense. Now, there's a question that we cannot answer by any experimental evidence on Earth. Even when you make neutrons matter and make it this extremely dense stuff, we still think that the quarks, the constituents of both protons and neutrons in normal matter, might remain bound. We've never seen a free quark. If we keep on squeezing matter further and further, do free quarks appear? So, can we ever reach a form of matter that we've never seen before? And does this happen in the universe? So think of taking a bunch of grapes and squeezing them further and further and further. As one of my colleagues likes to say, eventually you will get grape juice. So can we get to that point somewhere in the universe where we've squeezed matter so hard that the constituents of protons and neutrons have broken up to their original form, which is free quarks? So when I put this on some line, going from normal matter at lower density with its electrons around to neutron matter, is there this next step made up of free quarks? So from here to here, take a guess as to how many factors of 10 we have increased in density. Remember, from water to something like iron or platinum, it's a factor of 20, 20. From here to neutron star cores, where we think this matter appears, it is a factor of 100 trillion. That's why we can't make it on Earth. We can temporarily form matter. We can probe the constituents of the nuclei of atoms by smashing particles together, like Elliott Chu is going to talk to you about. But that's a very temporary state of matter. We can't make it sustained. And therefore, we can't say if there is a stable form of matter that actually is made up of free quarks. Okay? That we can only do if we find the right places in the universe where gravity comes to our help. Because whatever we can do on Earth is limited by the amount of force that we can apply to the particles. But out there in the universe, our sun, which is a pretty ordinary star, I know we don't like to hear that, but it's actually kind of a wimpy star. Imagine the amount of crushing force it can apply inwards to every bit of that star. There are stars that are 300 times the mass of our sun. So gravity plays a huge role in shaping everything that we see in the universe. And in that state, we think stable configurations of this dense matter that's 100 trillion times more dense, that a teaspoonful would weigh as much as the A mountain can actually occur. Dense just means more matter packed into a smaller volume. So that's how much it would weigh. Okay, so in order to understand what type of settings would allow us to reach that, let's just think for a second of how stars spend their lives. Actually, stars spend their lives fighting against this inward pull of gravity, this crushing force that they feel just by their own weight, the walls collapsing, trying to collapse onto them. But stars, during their regular lives, produce a lot of energy, produce heat, light, through nuclear reactions, combining hydrogen into helium, helium into carbon. That's what generates the energy that holds a star up. So a star is always a fight between the inward pull of gravity and the outward push of pressure. During their lifetimes, this pressure is always equal to the gravity, and it always comes from the fusion reactions that take place at the cores of these stars. But a star has a finite amount of fuel. Eventually, it will go through all of its elements, fusing them, and run out of the source of energy. When that happens, it starts actually collapsing and losing that pressure support that it has enjoyed through its life, and gets to a point where gravity seems to be winning. So at this point, when all these atoms are squeezed against one another and turned into this neutron-rich matter that I was telling you about, there are two options. Either those neutrons pushing against one another are going to win and stop the collapse, and we will end up with a neutron star, or they will lose this fight, and the walls will come crushing down on the entire star, and we will end up with something that shrinks infinitely to the core, and we will end up with a black hole. So thinking back to the very first questions that I tried to present to you as far as rethinking reality, I said, do our physical theories fail? And do they contradict each other? This is an excellent place to look, because you've pushed gravity to its extreme, you've pushed your understanding of particles to its extreme, and now they're in this fight for their lives, basically. So it's that interface that I've been studying for the last 20 years or so, ever since I was a graduate student. I've been fascinated with what happens if the outcome is a neutron star, what happens if the outcome is a black hole. So let's go a little bit further. First, follow the first path that I just mentioned, which is, let's say that the neutrons that are formed can stop the collapse. But there are still those nagging questions. Is it just neutrons, or do we actually encounter free quarks in that dense state? How do we answer that question? So it turns out, even though they are tiny, they are, give or take, 15 miles across. And even though they are very distant, so take the size of a city that's much smaller than Tucson, and put it at astronomical distances where we can't send probes to actually find out what's in the interior, it turns out that neutron stars aren't very shy about revealing what's in their interior. And the reason for that is the following. If the interior is pure neutrons, like in the first case that I showed you, it turns out they can withstand a little bit more pressure if they don't dissolve into their core constituents, and can make stars that are a little bit bigger in size and a little bit heavier, more massive. Whereas if they do dissolve into their quark constituents and become some sort of a quark star or hybrid star, then they cannot support as much mass, and they tend to be smaller in size. So what we've been trying to do is measure the sizes of neutron stars and the masses of neutron stars to see if they look more like this or more like this. Now, these are tiny objects, very massive but tiny and far away. So again, we can't send probes, we can't go near them. We'll have to use the light that's emitted by them and reach our telescopes either on Earth or in orbit around the Earth in satellites in order to answer this question. So what do? We weigh them. It's not that hard. How do we weigh the sun? We don't go there with a scale. What we do is follow the motions of things that are orbiting the sun, in our case, planets, and apply the same principles to things that are orbiting a neutron star. And use Kepler's laws. Kepler wrote down these laws several hundred years ago, and it works. This could be another neutron star orbiting around the neutron star. This could be a normal star orbiting around the neutron star, but the same principle will apply. So we weigh them. How big are they? Can they have quark cores, or do they have neutron cores? And we measure their sizes. Again, sort of like a ruler, but what we really do is collect all the light that comes from the sun. This is, again, very similar to what we do for normal stars. We separate that light into its components, into different wavelengths, and form a spectrum. And the combination of the total light emitted by the star, by the neutron star, and the breakdown of that light into its elements, the spectrum, gives us an exact measure of the size that is emitting that light. So this is a technique that we use, and in the past few years, we've actually made a breakthrough in this technique, both because of more sophisticated calculations and better data that we were able to obtain. And so far, all the data that we have point to smaller stars. So something more like 12 miles across as opposed to more like 18 miles across. We can tell the difference. It's mind-boggling that these faraway objects can differ by such small amounts, and yet we can tell the difference, but they turn out to be the smaller kind. So what we think is happening with the current data is that free quarks most likely appear in the cores of neutron stars. If this result holds, if we subject it to many independent tests, find other ways of weighing them and measuring their sizes, and we believe our result at the end, it would be the first time anywhere in the universe that we have evidence for a state of matter that is made up of free quarks. The second thing that this result tells us, all the data that we've gathered, is that anything that's more massive than about twice the mass of our sun is bound to collapse into a black hole. So there is no stable neutron star configuration or quark star configuration that will hold up anything against collapse that is more massive than about twice the mass of our sun. Okay? So the regime we're in is that we have now pushed matter, squeezed matter down so much that nothing can stop its collapse against gravity. So what happens? I said in that diagram a black hole forms, but I haven't really introduced black holes to you. In order to do that, I'm going to take a tiny detour and talk a little bit more about gravity and tell you why black holes are inevitable in our current understanding of gravity. So, of course, in order to do that, we go to our friend, Albert Einstein, who is one of the people who rethought reality in many ways, in almost all of his contributions. But probably the most phenomenal one is when he rethought gravity. Any other force, any other interaction in physics, we write it down as a force between particles. an interaction that takes place between two particles. Until Einstein came along, when we had Newton's formulation of gravity, the same thing was true. Gravity was an interaction between two masses, and that's how Newton's theory was formulated. However, when you look at Newton's theory, it's actually incompatible with special theory of relativity, which Einstein had worked out several years earlier. So he thought, these two theories contradict. That is a great place to look when your physical theories that have been individually tested start conflicting with each other. The discovery potential there is huge, and that's exactly what Einstein used in order to rethink our understanding of gravity. And what he said is that, actually, gravity is not a force at all. Gravity is just a geometrical bending of space-time. So, in some ways we can picture this, right? We can take a fabric, put 4 people in its corners, stretch it out, and then let's say we put a cannonball at the center. What do we expect? We expect that fabric to bend. So Einstein applied the same principles to now not just a normal fabric, but the fabric of space and time, and said, every object with a mass, let's say our sun, bends, makes these curvatures in the space and time around it. Okay? So in this geometrical formulation, there are immediate consequences. If you bend the space of fabric and time, so let's go back to our cannonball example. Now take a small marble and put it on that fabric. What is it going to do? It's going to go down that path. So it's going to follow that space-time, except that that space-time will be curved. So what Einstein said is that not only matter, but light will also follow these curvatures of space-time. So let's say that we are sitting here on Earth. We are looking behind our sun. The sun has bent the paths of all the light coming to us, which means that a star that is actually here and emitting its light in all directions, and some of it reaches us here on Earth, has to follow this down and back up of that curved fabric of space-time. Now, this is just like a lens. If you put a glass of water, it bends the light that goes through that water. So what's the net result? An observer sitting here on Earth would think that the light actually came from here, because we just follow it back in its path, and we would think that the star is actually here because of that bending of light. Okay? Kind of strange. Is it true? So this is now 1915. Einstein formulated this entire theory that explained some of the things that Newton's theory of gravity couldn't explain, but there was no experimental evidence that this was actually what was going on, until Sir Arthur Eddington took advantage of a solar eclipse in order to arrange an expedition to a small island off the west coast of Africa. And here is what they did. I know this is a little bit hard to see, but it's the original image, so I wanted to share that with you. This is now 1919, and what they said is that, okay, if the sun is in our line of sight and we are looking at stars behind it, then we should see this shift in their position, in the perceived location of those stars. Now, when the sun is up in the sky, obviously we can't see the stars behind it. That's why the solar eclipse was so important. It blocked the light from the sun for 6 minutes, enough for them to see where those stars are. And they compared this to data taken 6 months prior, when the sun was in the other side of the Earth's orbit, and they saw, I don't know if you can make it out, this shift in the positions of stars in the sky. This one is not visible, but hopefully you can see these. So this is data combined from the solar eclipse with those taken 6 months apart when the sun was in the other direction, when it wasn't giving this curvature to the space-time in front of us. So this became instant success because seeing is believing, and it was on the cover of all major publications of the time. Basically, the day after Sir Arthur Eddington took the data, Einstein became an instant success, and this is the cover of the New York Times from 1919, and men of science more or less agog over results of eclipse observation. So basically, it changed people's worldview that, yes, this geometrical formulation of gravity is the right one, and Einstein's theory is correct. So if it naturally predicts this, what we call gravitational lensing, in the sense that paths of light are bent and masses act like lenses, just like the lenses that we know that make things look distorted. So if this gravitational lensing happens, then we should be able to see it elsewhere in the universe. And indeed we do. One of the places that we see this beautifully is clusters of galaxies, where there is so much mass packed into a small volume that all the background galaxies are lensed, and this is a Hubble Space Telescope image showing the giant blue arc. It's also called an Einstein ring. This is actually one galaxy that happens to be behind this galaxy cluster. And because light is now coming to us from all directions, encompassing that galaxy cluster, we see it as a ring in the sky, even though it's one point object behind this cluster. So gravitational lensing happens. Take this to its next logical step. Now, I have a neutron star. I have packed so much matter into a small volume. It's going to curve the space-time around it pretty drastically. What if I cross that one extra step and put so much matter in that now it's collapsing inwards and all the light paths are bent inwards? I mean all the light paths. There is no light that's approaching that object that can make its way out. So they're lensed inward so much that they're absorbed by that mass. That is what we call a black hole. Okay? So let me just show you, if we were able to take a journey physically into a black hole, what our computer simulations, actual calculations, would show as far as what our journey would look like. So we're going to now, in the next movie that I'm going to show you, dive into a black hole. On the lower left corner, you're going to see our trajectory. We're not going straight, we're kind of taking a swirly path, and we're going to cross that point of no return, called the event horizon, okay? And even though it looks like the black hole is moving, actually what's happening is we are moving. This is our trajectory. And this is just the grid painted on there. Of course, you wouldn't see this if you were falling into a black hole, but it's there, just to make it clear. But it's there to show you that, for example, you would see the two poles of a sphere at once because everything is bent inwards. And we're approaching the horizon. The red circle here is the horizon. Look at what happened. All the lines that were behind us and all the lines that were in front of us now collapse into one. We're now in the singularity. Okay? So it would look something like this. And if I could, I would go and enjoy it. I wouldn't be able to report back to you what it looks like. And I don't think I can convince a graduate student to go. So we're going to do the next best thing, okay? We can't go there, but we know what the black hole should do to any light that is around it. And we've known this since the 70s, actually. There are calculations, literally hand-drawn diagrams and long pages of calculations, calculus, that people have carried out as far back as 1973 to tell us the telltale signature of a black hole. There is something that is uniquely predicted by the existence of a black hole, and that is that shadow, that silhouette that it leaves on the light surrounding it. In the early calculations, the pen and paper calculations, they imagined a source of light, somebody kindly holding a flashlight behind the black hole for us, and what it would look like, if this was the black hole, what it should look like if we could take a picture of it. Okay? And what they said is that there should be a bright ring of light, and interior to it, there should be absolute darkness. That is the telltale signature. It's a shadow, it's a silhouette, and that would define that point, that presence of the event horizon where we are disconnected from the universe, where the rest of the black hole is disconnected from the universe. Again, why are we looking for this? Let's think back to some of our questions. We now want evidence that this actually happens, not just gravitational lensing happens, not just that the photon paths are bent. This is a logical conclusion of general relativity. It's almost inevitable. And yet, at the same time, it is so bizarre. It is bizarre because it's predicting regions of the universe that are completely disconnected from the other regions, that information goes in but doesn't come back out. And two, it actually contradicts everything else that we know about particle physics. Because in particle physics, where we formulate things as an interaction, as a force, what we say is that if I combine two particles and make a third one, the reverse reaction should always be possible too. It may not happen often, but it should be possible. If I go in this direction, I should be able to go in this direction. Clearly, that's breaking down here. I can go in, but I can't come back out. So if I now try to write the laws of particle physics around the event horizon, I get nonsensical results. Again, our theories are clashing with each other. Even though they are individually well tested, they're taking us to a place where it might be fruitful to really look at, is physics breaking down? Do we have to rethink reality? Okay? That's what's so attractive about looking around black holes and looking for signatures of this black hole event horizon. As time went on, in about year 2000, we started doing more realistic calculations where somebody didn't have to hold a flashlight for us. But the source of the light was actually the hot gas that's swirling around the black hole itself. Because black holes have such a strong pull, they pull gas from stars or clouds or whatever might cross their path around them. And as this matter swirls around and makes its way towards the black hole, it heats up because it's gaining so much energy from this gravitational field that it heats up and starts emitting light. So we started being able to do somewhat more realistic calculations right around the year 2000, and this is one of those images. Now, instead of a donut like you see on this one, this is more a crescent. The reason for that is the light is no longer uniformly coming from the back, but it's coming from the swirling hot plasma, which means that the part that's moving towards the observer is brighter, and the part, just like an ambulance siren that is higher pitch when it comes towards you and lower pitch as it's going away from you, one side becomes brighter than the other. So instead of looking for a donut, we should really be looking for a crescent. It still has this other side, but it should really be brighter here. Now, since the year 2000, a lot has happened, And a lot has happened both on the experimental side, where we actually started a campaign to take a picture of a black hole, and on the theory side, where we had to know what really we're looking for. Everything that I've shown you so far has been highly idealized. So if you wanted to now take this concept, that is, look for the shadow of a black hole, take a picture of it, and apply it to a real-life experiment, you would fail because of all the complexities you haven't taken into account. So what we have done here at the University of Arizona is develop new computational techniques, new algorithms, that allow us to do these calculations millions of times faster than it has been possible before. And in fact, it has been such a breakthrough that I want to show you not an animation that we did with it, but a movie of one of our research associates, C.K. Chan, actually running the simulation in real time. And we filmed him running the simulation. Okay? What made that possible? What made it possible is that little graphics processor unit that you have on your phones, on your laptops, instead of the CPU, we now started using the graphics card, GPUs. And it's almost like writing a computer game, except that it's not. It's solving equations of general relativity. But making use of that graphics processor unit, as I said, we sped it up many, many orders of magnitude. So what you're going to see here is this hand, and there is a motion sensor device that's sitting right here. We programmed it so it would read hand gestures like your Wii or Xbox. And this is the black hole. And he's going to shoot 1 million photons, 1 million rays of light at this black hole all at once. Okay? So let's see. He's initializing the simulation. He's running time forward. So you see that wall of light running and being rendered visually in real time. Now we can zoom in and look at all the light that's already trapped around this black hole. Their paths have been changed. Some of them already went in. Some of them are just circling around the black hole, depending on how close they came to it. Running time forward again, and now running time backward. Why not? We are allowed to do that, right? It's a computer simulation. So now he's going to zoom back out, and you're going to see the effect of this black hole on this. So these are all the light rays that traveled a little bit longer and got left behind. And when we run time backward and zoom out, there it is, the shadow of the black hole. Now, again, this is highly idealized, but I want you to understand that this is running on his laptop, on a single GPU. And our goal is to be able to scale this up and really look at swirling hot plasma around the black hole and calculate this for every situation that we can think of. And in order to take it from this realm of theory into what is really experimentally visible. So in order to do that, of course, we couldn't rely on individual GPUs on laptops. So the University of Arizona, a number of us, applied for a National Science Foundation grant, and we brought a GPU cluster to the University of Arizona that we lovingly named Elgato, the cat. And that was a major breakthrough. Even this amount of investment in computational facilities, in hardware, in theory, really gives enormous results. With this, we were number 7 for a small period of time on the world's Green 500 list, meaning the highest number of computations you can do with the least amount of energy spent. These glories don't last very long in the computer world, but still we were super happy to be number 7 in the world here at the U of A. And this allowed us to really scale up our game. And as I said, take it from that realm of this is what general relativity predicts, this is what our theory of gravity predicts, to, okay, let's turn this into a real experiment. I'm going to skip this. So, what do you need in order to take a picture of that shadow of the event horizon of a black hole? You need a few things to go in your favor. First one, it's kind of obvious. You want the Earth's atmosphere to be transparent. If you know some wavelengths of light can't penetrate through our atmosphere, so we would like to do this experiment at a wavelength that can actually make it through our atmosphere. Okay. We want the galaxy to be transparent. We're going to be looking for nearby black holes and the light emitted from them to look for this crescent or donut. And we are going to snap a picture of it. So if the light doesn't make it to you between the black hole and your telescopes, then you're not going to get a good picture, as every photographer knows. There is another component. We've been talking about this hot gas swirling around the black hole. And what if that obscures your view? So you need to pick a wavelength where you have enough light so that there is this shadow forming against that backdrop of light, but it's not so much that it's obscuring your view. You need to be able to see down. So this is one of the simulations that we've done using Elgato. What you're going to see is we're going to change the wavelength at which we're looking at the black hole. Initially, you'll see this huge plasma blocking our view, and as I run this forward and increase the frequency or decrease the wavelength at which we're observing the black hole, what you'll see is at right around 1 millimeter, this crescent appearing here. Okay? So 3 requirements. The atmosphere to be transparent, 1 millimeter actually fulfills that criterion. The galaxy to be transparent, 1 millimeter is a good wavelength to look at. And the plasma around the black hole to be transparent so that all you see is that crescent, 1 millimeter fulfills that too. It's a very lucky coincidence. And we've been working, again, with all of these types of simulations at very large scales in order to look at any complexity that might come our way. So there's a 4th requirement, which I didn't write down, but it's kind of obvious. This thing that you're looking for should be big enough in the sky for you to be able to see, right? So you might think, well, where's the closest black hole that we know of? Is that what we're going after? There are about 30 black holes that we know of in our galaxy that we definitively know through other means, for example, stars circling around them, that they're black holes. Most of them, all except one, tend to be about 10 times the mass of our sun. So they're kind of close, but they are very, very small, which means that the size in the sky is not something that we can measure. But there is one black hole at the center of our galaxy, the center of Milky Way, called Sagittarius A star, Sag A star for short. And that one, even though it's farther away, it's all the way at the center of our galaxy, it actually fulfills the requirement of being large enough to be visible to us, as long as you have an Earth-sized telescope. How hard can that be? Okay, so our best target is Sagittarius A star. Its shadow size, for those of you who actually know the sizes of things in the sky, is 50 micro arcseconds. How tiny is that? That's like putting a donut on the moon and saying, take a picture of it. That's how big it is in the sky. But again, if you have an Earth-sized telescope, that's okay, you can do it. Unfortunately, the National Science Foundation gives us money for Elgato, but for some reason not for an Earth-sized telescope. So we go to the next best alternative, which is we pretend we have an Earth-sized telescope. What that means is that we hook up telescopes that are scattered across the Earth and use a technique called interferometry. The name doesn't matter. All it means is that you're looking at a distant object, in this case, your crescent with your shadow, and you're looking at it with telescopes across the Earth at the same time. And you're recording your signals with such high precision with an atomic clock, which are the hydrogen maser clocks that are at each radio telescope. And you're recording so much data as these wavefronts come in and hit your telescope that after the fact, you can take these data drives and you can combine them and look for a signal of where they match up. Where they match up, you get this booming signal, and that tells you how big was the object that emitted it. Okay? It's like treating the Earth like a telescope dish. Obviously, you're not going to have the collecting power of that dish, but you're going to have the resolving power of that dish. Okay? So we then send this to correlators around the, right now in Cambridge, Massachusetts, and there is a backup one in Germany. And we've been building this, this Event Horizon telescope, both the array and the collaboration and all the data analysis tools and the theory for about 15 years, starting in year 2000. And Arizona has been involved since the beginning, not just for the theoretical calculations that I already told you about, but also because of our sub-millimeter telescope, this 1 millimeter, this telescope that allows us to do the 1 millimeter observations right here in Arizona. So the array over the 15 years has grown to include these 9 telescopes that span the Earth from the South Pole to the Atacama Desert in Chile, to Mexico, to Arizona, Hawaii, and a couple of stations in Europe. And some of the dishes existed, other ones we had to outfit. And here is the principle that we're operating under. We're going to look at, as the Earth rotates, we're going to be looking at it with as many subsets of these 9 dishes as we can at any given time, record the data, and then combine it in order to form the picture after the fact and see if the shadow is there, and if it's as big as general relativity tells us it is. It's a very clean experiment in some ways. There is no wiggle room. The donut needs to be there, the crescent, and it needs to be a particular size. So for some of the telescopes that the dish was there, but the appropriate receiver in order to, that we needed to use in order to record the data were not there. This is another U of A contribution to the Event Horizon Telescope. My colleague, Dan Maroney's lab here in the astronomy department, he's a professor, and he and his team have built the millimeter receiver for the South Pole telescope, all shiny. I mean, obviously, how beautiful is this? Gold is a very good conductor, so it just keeps the temperature uniform across this receiver and reduces the noise that you get, but I just like it because it's shiny. So he once in a while lets me in his lab and I look at it, but not anymore because they have taken it down to the South Pole. This is now Dan on a balmy day. He's thrown off his jacket, and this is how we treat our graduate students. This is Junhan Kim, who slaved away on this instrument for about 3 years now. It's really a beautiful success story, and this is the purple cover that they put on that receiver. They're installing it in the South Pole telescope dish. The South Pole telescope dish does many other experiments, but it is part of the Event Horizon Telescope array now with the addition of this receiver. They did some testing. This is between the Apex and the Atacama Desert, one of the telescopes that is in the array, and the South Pole telescope. And as I said, when it works, when the two stations can record the data faithfully and then combine it after the fact, this is the kind of signal that you get. And obviously, this has been a success story. So what we expect to see for Sagittarius A star, this is now a movie rather than a still. Because of the plasma swirling around, there are some fluctuations in the brightness that we see, but ultimately, that crescent is always there. So now if I combine all of these images and show you what the computer simulation should look like, and now pretend that this was processed through all 9 stations and recombined, then this is what the expected data looks like. We are all ready. We are ready from the getting the 9 stations ready point of view. We are ready from the data analysis point of view. And our first full array observation is going to be in the first week of April. Yes, Thank you. Keep your fingers crossed because we need good weather in 9 stations. And if we can't get it all this time, obviously we're going to keep on doing this experiment now that all our tools are ready. But April is around the corner. I'm going to be at the SMT, even though I'm not needed, I just want to be there. And hopefully we're going to come up with something that either proves the theory of relativity or even better, maybe conflicts with it, maybe shows us some signs of where we should be looking when we rethink reality again. Thank you.